This is lesson 77, VHDL example 49. And in this example, we'll use VHDL to design our 3-bit counter. You remember from the last lesson, this was the state diagram we had for a 3-bit counter, where the states just count from 0 to 7 and then repeat. And this was the logic circuit that we derived in the last lesson. We had 3 flip-flops in this combinational circuit to produce this 3-bit counter. Let's go ahead and implement this one in VHDL. We have a clear and clock coming in and the 3-bit Q going out, 2 down to 0. Then we'll define the signals D and QS. Here are the logic equations for D2, D1, D0 that we derived from Carnot maps in the last lesson. And then we'll make the 3 D flip-flops. We'll have a process, clock, and clear. If clear equals 1, we'll set the signal QS to 0, 0, 0. Else, if clock tick event and clock equals 1, remember this is the rising edge of the clock, QS gets D. So this is just the 3 D flip-flops, where the input D are given by the logic equations we derived from the Carnot maps. We set Q to QS, and this should be our 3-bit counter. Well, if we simulate it, we see that in fact it works. Here is the clock, here's the clear, which initializes Q to 0. Then on the rising edge of the clock, we go, Q becomes 0, 1, 2, 3, 4, 5, 6, 7, and then restarts at 0, 1. So it counts from 0 to 7. Look at the waveforms for the output Q. Here's the frequency of the clock. Q0 is also a square wave at half the frequency. Remember, we saw this divide by 2 counter before. Q1 is half of Q0, you see. So that's a quarter of the original clock Q. And then Q2 is also a square wave at half the frequency of Q1, which means that's going to be an eighth of the frequency of the clock. So for every period of Q2, we have 8 clock periods. That's why we call this a divide by 8 counter. So this 3-bit counter is a divide by 8 counter. Now, as you might expect, in VHDL there's an easier way to make a counter than to use Carnot maps and derive the logic equations. Let's see how we do it here. Here is the same 3-bit counter. Clear and clock in. Q is 2 down to 0. There's the output. We'll define a signal count, 3 bits, standard logic vector 2 down to 1. And then we can just make a process with clock and clear in the sensitivity list. If clear is 1, we'll do an asynchronous clear of the output. Count will be 0, 0, 0. Else, if the rising edge of the clock, then count is just count plus 1. A counter is just incrementing the output by 1 on every rising edge of the clock. So we can just put an adder here. Remember, this makes a full adder. We'll have 3 of them, 1 for each bit in the count. And so this is how count behaves. It just counts, and at the end we'll set the output Q to the signal count. So if you compile this and simulate it, sure enough you get exactly the same counter we had before. Here's the clock, Q count 0, 1, 2, 3, 4, 5, 6, 7, back to 0, and we have the same 3 waveforms we had for the output Q.